there exists a very simple solution for this. Start a counter variable at 0, go through all the assignments. If it is a model, update the counter. If not, don't update the counter, right? So this is a p-space problem. Now, how do you prove this? Like in your elementary schools, like you show your proof, right? Show all your working. Like you can plot a graph. This is a cumulative function graph. This, if you once show this and it's correct for every point, it is definitely a correct proof for model counting, right? But as you can see, there are exponential assignments to go through. So we will be clever about it. We will not go through exponential assignments, right? So basically, this is the motivation of our system clip. We're going to introduce it soon. Right. Before that, what are the existing systems in proof complexity? There are three main systems here. First introduced was KCPS, knowledge-based compilation proof systems. These have a decision DNNF as a base. This is a static system. So given a formula, it will need a decision DNNF and a proof that the decision DNNF is equivalent to the formula CNF given. So, and model counting is easy in decision DNNF, so this is a valid system. And next system to be proposed was mice model inductive something. Okay, yeah. Now this system was actually a line-based system. This is dynamic. It gradually, by 3 or 4 rules, it has sound rules. It will derive the final line where you don't have any restriction. You have the final model count. But this system does not have any structure, right? This is a line-based system. But we will see that this actually depends on a structure, same decision DNNF. Why? Because in the next paper, they prove that mice can, a decision DNNF can be efficiently extracted from a mice proof. So definitely it is bound by the size of the decision DNNF for a problem, right? So these two systems were bounded by structures. Then the third system defined was CPOC, which is recently defined. Now, this system has, again, similar to a static system like KCPS. This has a POG data structure, partitioned operation graph. And in knowledge compilation, I think it's equivalent to DD structure. It's quite powerful. We do not have any lower bounds right now, but still, it's a well-studied structure. Again, similarly, again, you have to show that POG is equivalent to the CNF file, right? Now, but what is the basic point of the slide is there is an underlying circuit in all of these systems. So we will not run that, right? Because definitely lower bounds of the circuit will lift to the lower bounds of the system. Now we will give a system that there is no restriction on the circuit that you're using. But there is a what is the concept? As we saw in the first slide, we will make a cumulative function of any formula that you give us. So that function we will represent as a circuit, and this circuit will not have any restrictions. The only restriction is obviously that it has to be correct. We will see that next. And that model counting will obviously be easy in this. Why? Because as you saw in the graph, the last, if you provide it with the last possible assignment, we give you the total count that you want. That is the one, right? Fine. Now we will motivate this system with an example. This is an XOR pairs problem, which was proven to be an exponential lower bound for mice system. So now, but this problem is very simple actually. There are like x variables and n square z variables, and this is the only clause. So if you fix an ordering between x and z variables, let's say x comes first and z comes next. Now you can see the type of models that are in this system, right? Because once you fix an ordering, once you fix the assignment for x, there is only one possible assignment for z such that the total thing will become a model. So how many models are there? 2 per n, because all assignments of x. Now, this is seems a very simple problem. Cumulator can also be simple for this. What you need to do is, let's say you're given, someone gave you a complete assignment, alpha, comma, beta, x and z respectively. Then you will take this alpha and you'll find out the XOR equivalent beta prime that would have been a model. And then check if the beta given to me is after this beta prime or before. Once it's after, that means you will have to plus one in the count, right? Or if it's not, then only some number of models have come before this assignment. So you see how we've reduced this to just a 3-step problem. Like you just calculate the XOR equivalent, then you do if else. This is all easy in circuits. So it's easy. So this was an easy cumulator. But now, what was the catch? Well, it's not really catch, but you have to be sure, right? I've presented a proof that this is true. But how will a system know? This cumulator different from any random function. So we have to certify the cumulator. And the base case and final case are easy to check, because when the base case, if 0 is a model, it should be 1. If not, it should be 0. The answer returned. So then the remaining cases can be written as an inductive step. Like if y comes after x, the model count returned should be exactly equal to x plus 1 based on if it's a model or not. Is it simple? See, if y comes after x, just after x, then the model count should only increase by at most 1, and that 1 should depend on whether y is a model or not. This is just statement is just saying that. And this, you can see, is just a CNF formula, right? This x and y are set of variables, okay? But you can see them as 1, because we are going to represent them as a sequence of all assigned, right? So this is just a friendly problem. So you can just use a nice propositional proof system to prove this once you have the cumulator. Now we are coming to our system. So our system is CLIP, circuit linear induction proposition. And this is actually modular system. So you can do a plus some propositional system. So what will our proof in a system CLIP include? It will include a cumulator circuit and then correctness proof in the set proof system of this LIP statement. Let us call this LIP. Then what system do we use for propositionals proof system? We can use the most stronger, right? So that would be E-Frege. That is nothing but Frege. Frege you all must have known. It is a textbook style system, and it actually is able to simulate all types of solving methods or techniques. Now, extended Frege has just an extra, you can add new variables to it, which represents another, again, some formula of CNFs of existing variables. And it is known that T-Frege has no lower bound set, and this is an actually major open problem in the complexity class. So it's easy to find proofs in this, and we actually, the same cumulator that I explained, we have a proof of it in E-Frege also. So we prove this in our paper. So this will become a upper bound for the whole CLIP plus E-Frege system. Actually, this point was raised as an open problem in the previous year paper, and we've solved that. Now, why is this system so powerful? There should be a reason, right? So we give a reason that it is a conditionally optimal system. What we mean by that is, if someone finds a lower bound in our system, they have solved some major open problems. Specifically speaking, they have either shown that E-Frege has a superpolynomial lower bound, but P sharp P does not belong in P poly. And to just recap, P sharp P is just all the problems you can decide with Sharp oracle. That is a sharp set, the problem we are trying to solve, right? Then, P poly is all the given functions which can be represented by polynomial size circuits, right? Now, the proof is also pretty, proof argument is pretty simple. Like, let's say someone found a lower bound in our system, phi n, okay? Now, if you see the cumulative function of this phi n and then consider the bitwise part of it because it will be a functional one. So, consider bitwise of this cumulative function. That definitely is in P pi sharp P. Why? Because if you give an oracle to this, it will give you the whole answer, you just pick the bit you want, right? Now, suppose P pi sharp P is not is belonging to P poly. What does that mean? That means a circuit will exist, a polynomial circuit will exist that will represent this function, right? And that function is nothing, that is what we want, right? That is the cumulative. So a polynomial size cumulator is existing. So now, and the lip statement was just polynomial in the terms of cumulator and the original formula. So that means you have come to the lip statement. Now the only, but it is still a lower bound of our system. So that must have been a super polynomial lower bound of P again, right? Either that has to give or our assumption was wrong, right? Which both are the major problems. So the system is powerful. I mean, there might exist lower bounds, but you cannot find them by mistake. You'll solve some open problem. Now, one advantage of existing systems we have is for unsatisfiable formulas. What will be the model count of unsatisfiable formulas? 0, right? So that should be a very easy case. But no, mice and KCPs have been shown equivalent. Like mice was shown equivalent with resolution when it comes to unsat formulas. And KCPs was shown to even restricted regular resolution. Only in case of unsat formulas. But both these systems have very much, many lower bounds have been proven, right? So we do not want that. And in case of CPAC, actually, it's not very clear what it does in unsat formulas. But our system has like, we give this proposition that if there is a short E-Frege proof, then it should have a short clipless E-Frege proof. And it's actually easy to see also, we don't include the proof. The proof is simple because the lip statement says, you can have a trivial cumulator here, right? Cumulator always outputs 0. You just have to prove that it's correct. Then the lip statement actually reduces to this CNF formula. Then that will be the Frege proof, right? Now, actually, this is an interesting thing. We come up with a technique to simulate any sharp-sat proof systems. And we have tried for all three, it will work. So this is a general framework. Given a proof of some system, how can I get a proof in clipless E-Frege? Right? That's the question. So now this is done in two parts. First, you extract the cumulator from that circuit and then you prove its correctness. We'll give procedure for both of them. Let's see cumulator extraction, right? Now, yeah, first, let's say we are considering some P system. Then we will have some proof of it. You have to first step is to prove that the system is closed under restrictions. I think many of you know what it is. It's just basically given a proof. If you have some assignment, some partial assignment or complete assignment, you follow that in the proof and you restrict all the lines where it is not consistent with this alpha. And then you have to get the final count equivalent to phi restricted to alpha. So if you restrict the proof with alpha, you should get the count also equivalent to the phi restricted by alpha. So this is also known as conditional knowledge compilation, if you're from that row. Now, so this can be reset in the way like that, right? It's like you get a function theta. You can extract a function theta from a proof such that if you give any assignment to it, it will give you the model count of the phi restricted to that assignment. So from now, theta means this function. It's just given any assignment, it will calculate the model count of the restricted formula. Now, but we still want the cumulative count, right? Given some alpha, we want the count from 0 to alpha. So, but alpha can be theta, we don't want to strictly all formulas, right? So we come up with a way to find partial assignments that cover the entire range of 0 to alpha, and which is not exponential. In fact, we find out a way that it will become linear. It's based on a Fenwick tree algorithm. If you know binary index tree, I'll come to it if time permits in the end. Okay. So this example you can see, if alpha was 1101, that is 13 in binary, right? Then we can consider these assignments like x4 is 0. Once you restrict x4 to 0, it will give 0 to 7 assignments, right? Then I'll restrict 1 and 0. Then that will cover 8 to 11 assignments. Then I will restrict 3 variables that will cover 12 and 13. Now you have finished all the space and you do not have to go check 13 assignments individually, right? Checking these 3 assignments would have been enough. So now the final algorithm is exactly that. Given an alpha, go find its Fenwick assignments, that is the partial assignments covering all of these 0 to alpha, and then you just add those counts because that's what they're supposed to give, right? Once you restrict, it will give the count of phi restricted to alpha. Just add all those counts, that will be your required answer at the end. So this is all polynomial time steps. So you will get a polynomial size circuit here. Now, this is correct. How do we prove this? For this we say there are yeah. First of all, the circuit is the one you just extracted, right? Only in this method you have a proof. So that proof is we actually formalize the EFG does not believe restrictions, properties of restrictions, right? So we actually have to prove that properties of restriction actually hold in this system. That is, we formalize the property sections as 2 statements and then have their EFG proofs, and then that we give a theorem to translate it to the lip statement proof in EFG. What are properties of restriction? These are very intuitive 2 properties that actually capture the statement that a proof system is closed under restrictions. That is, it's clear, right? If theta is a function, initially theta is a function that given in alpha, it will give you the models in phi restricted to alpha. So intuitively, if alpha is complete, it should give you 0 or 1 based on if it's a model of the formula. That is first property. The second property is, let's say alpha is strictly a partial function, and it is like in a sequence it has given all values, and after I, it is not assigned any other variable. Now we say it should be able to, the number of models of phi alpha should be equal to extending this alpha with both 0 and 1, and then adding them, right? So these are trivial properties that give you this formalizing the concept, and we want infinite proofs of these properties in the system. So yeah, so once you know that the proof system is closed under restrictions, it definitely satisfies these conditions. That is easy to see, but you have to find the proofs of them. And we did this for CPOC. So this has so that gives us keeps us in the top of the hierarchy, right? So we can simulate CPOC, and CPOC has already separations shown. So yeah, so to sum up, these were the problems, right? We have shown XOR pairs is easy here, and PHP and click are also easy because they are easy in resolution. So I'm sorry, they're hard in resolution, but they're easy in EFG. So they're easy in our system. Again, the situation in CPOC is not clear, but we hope that clip is greater than CPOC in strength because it has an underlying circuit with it, right? So one day they might find lower bounds of a structure, but ours is an unrestricted circuit. Do you have time?
Yes.
Okay, so let's quickly go to the Fenwick assignments, right? I think many of you know this as a binary index tree or a Fenwick tree. This is basically, it is to represent array, a cumulative sum of an array in logarithmic steps. But here our assignments are exponential, so logarithmic of exponential, we have linear number of worst case assignments that we can get. Okay, so this structure is very, it's simple. It's basically binary values of all these numbers. If you see, every child is just different from the parent in one bit. That's it. And the number on the edge is the bit number that it is differing with. Okay. So, but here the 0 is a dummy node actually in Fenwick. So, but our assignments start with 0. So, we actually take +1. Like if I wanted to find alpha is equal to 13, I go search for 14 in the tree. Okay, so how it work is, it's simple. You go from 14 to the root in the tree. Like and note down every parent along with its edge. Like from 14 you have 12 comma 1. And from 12 you have 8 comma 2. And then you have 0 comma 3. Right? So we have just noted this down. And again we write this in binary form. 12, 8, 0. And then cancel out the number of the second number of digits from the right end. Like from 12 comma 1, you just cancel out 1 0. Then you cancel out 2, right? So basically what this is just a partial assignment. Like we are just restricting x1 with 1, x2 with 1, and x3 with 0. So that, if you can see, will give us 12 comma 13, right? It will represent. And similarly, right, here also we are just restricting 1 and 0. That will give us 8 to 11, all assignments possible. Now, using this, we prove that theorem that properties of restrictions will imply proof of properties of lip statement. This is easy to see in case of even odd, like is let's say 11 and 12 in this graph, but we have to take +1, right? So 12 and 13. So you can see 12 and 13. That is just the assignments of them. Just one more assignment is adding for 13. And it's always the case with odd numbers, as you can see. Odd numbers are immediate children of their even numbers, because obviously just the last one digit is changing, right? Always. So what will this imply? This will just imply this, right? If you give Fenwick, you're just given any assignment, you're going to take the Fenwick assignments, you're going to restrict the circuit with that, and then you're going to add them up, right? So sigma of 12 would be sigma of whatever 11 gives plus the extra 12th bit. That is evident from the structure Fenwick assignments that we're getting. So this will again lead to a lip statement. So half the problem is done. Now the other half is also similar, but it's little extensive. Here the both properties will be very apparent. Like if you see between 11 and 12 in the graph, 11 is here, 12 is here. They're in different branches, so they'll get different Fenwick assignments, right? But somehow they have some same assignments. If they don't also, they at least have this dummy node as their same assignment, right? So in this case, this 11 and 12 converge at 8. So after 8, they have one common assignment, 0 and follow with all them. And this is the new assignment that is not there previously. So, but we have property 2, right? We just expand this assignment with 0, 1. And again, and you can see that this first one is what we already have. So we just want this second one to expand it, right? After doing that, you have all the Fenwick assignments of the previous one, plus the only extra one was the exactly 1011, that is 11, right? So you have again 8 of 11s, 10 plus based on 11 if it's a model or not. So you again went to the lip formula. So this was about how we transfer in-figure proofs of properties of restriction, in-figure proofs of lip statements. So if you can follow these two methods and any new proof system comes into existence, you can try and simulate it with CLIP. And yeah, this has a future work. Actually, there are benchmarks possible on this, because now if someone gives me a formula and the accumulator of it, the loop statement is just a CNF formula, right? So we can maybe encode some hard formulas and cumulators, and we can see how that works as SAT benchmarks. Another is for DQBF also. So if you don't even know the cumulator, we can just encode the problem and the cumulator as follow, like there exists some cumulator and X is depending on only the X variables, and the Y part is depending only on Y variables. And then the certifying decision DNF solver would give us the cumulator in turn. So yeah. So I think that's it. Thank you. Any questions?
Okay, time for questions then.
Okay. Yeah. So what are the problems that you're looking at now?
Like for
What is your next work?
next work is actually in the first slide, if you remember, I told you this is a p-space algorithm, right? But we are not really using that here. So generally, our Leroy is actually lifting the systems to any problem in the p-space. So such systems can exist for any problem. So that is one way, and we are trying to make a system for MaxSat based on knowledge compilations because they are able to solve sharp SAT system, so it must be powerful.
Okay, so let's thank our speaker again.
Okay.
So the next talk is by Karthik.
How long?
Yes.
The third box slides are.
This is
This is for forward.
this
This is for backward. It's a point. Okay, and please take this one.
All right.
Mine.
Okay, we may start.
Hi, everybody. My name is Karthik. This talk is on oblivious complexity classes. This is joint work with Ilya from Boston and Zeon from NUS. It's not a very technical talk. Just ask me questions as they come. Okay. So what is the motivation of this paper? It was like, what is the power? We wanted to capture the power of non-uniform algorithms, or as complexity we will call circuit load bounds, right? And so, what is a non-uniform algorithm? It's just so if I think of a normal algorithm like a BFS, if I give you a graph of 100 vertices, 1,000 vertices, the algorithm is the same, right? A non-uniform algorithm just says, well, actually, I'll give you more power. For every input length, you can come with the algorithm of your choice. So it's strictly a stronger model. And it's interesting because like already here we can solve some really nasty things. We can solve the halting problem. Like non-uniform algorithms can solve the halting problem. Moreover, like since it captures uniform algorithms, P is a subset of 2 power. I'll define this in a second. And so if you could prove like lower bounds against this non-uniform algorithms, they imply lower bounds against uniform algorithms. So if we could prove that NP is not going to NP power, that implies P is not equal to NP. So the most natural question is, how far are we proving something like this? It turns out we can't even prove that non-deterministic exponential time isn't P poly. So this is like our Waterloo. In fact, every day that like we don't prove P is not equal to NP, Papadimitriou invents a new TFNP class. And that's why we're going to see like a bunch of like weird complexity classes. Like, if something doesn't make sense, ask me a question because it's a very simple result. There's just like maybe it's masked in like jargon that is messy. Okay. So what is with it? It just and or not gates. And I have some Right. So I have a collection of and or not gates, and I want to compute some function. And the measure I use is the size, which is the number of and or not gates and a number of and or gates I use. Okay. It turns out that this is actually a very robust notion because I can simulate any like Turing machine with just a logarithm law. So circuit size is a great estimator of time. And we use P5 to just kind of classify polynomial time non-uniform algorithms. And this is just notation. Right. So what, like, in terms of proving low, what can we show? Because proving low is hard. We have some information. A random function is hard. Small circuits cannot compute this. So you can just use by counter argument. They're very small, they're very few circuits, and there are many, many functions. So most functions cannot be computed by a small circuit. Okay. And the problem is, I guess, let me go back. The problem is that a random function is not explicit, right? Because every time I sample a new random function, it's a new function. It's not the same function. And the goal is to output explicit. When you prove a low bound, we want to prove an explicit low bound. Here's a function that's hard. Sampling is even a specific function, right? It's not a random function. SAT is a specific function. It's not a random function. So notice a specific function is hard. Like, that's the way to prove low bounds. And so Karan showed that, like, if in sigma 3, so sigma 3 is the third level of the hierarchy where you give an exponential time. That's what this means. Like, in that time, I can find the hardest function. Like, I can find functions that cannot be computed by small circuits. Awesome. But then after that, we couldn't get any further. Like, we cannot even show that a class e to the NP, that's exponential time with an NP output, is contained in circuits of like linear size. That's crazy, right? Like, we don't really SAT is in this, but we can't even show that e to the NP was much bigger. Doesn't have linear circuits. That equivalent low bounds. Right? So what can we show? Okay. So we got the higher region. Let's see what happens in the low region. We got some progress here. And so for now, we have this conjecture about non-uniform algorithms. Maybe non-uniformity is more powerful, right? So how would we quantify this? Maybe there is just some k for which we can capture all polynomial time computation. So there's some fixed k like n to the 100, where non-uniform algorithms running in time n to the 100 capture any problem in P. So I have a Turing machine that runs at n to the 1000. It's equivalent circuit, the circuit that solves it in n to the 100. Maybe there's some k that other bounds this. Doesn't seem to be likely. Let's try disproving this hypothesis. And in that, we'll come up with on fixed polynomial circuit low bound. So given you want to take some complexity class C, whatever it is, like and you want to show that for every k, it's not contained, there's no circuit inside n to the k sort that contain that class. And this is weaker than proving something like a polynomial low bound because you're giving a low bound for every k, not for the whole union. Okay. So again, in this class, Kanan's result works for sigma 2p, which is your second order polynomial hierarchy. There's a weird class, I'll define this later, S2p. And that's kind of the lowest class that we can prove these kinds of low bounds. And if you start allowing like one bit of advice and you get like really janky with the then you even get that any one bit of advice has this, but we're not going to go there. This is just something in that direction. And so if you look at kind of the known inclusions we know, sigma 2p is like the big class for which we have circular low bounds, and we prove these kind of circular low bounds up to this stuff S2p, right? The one is can we prove more, right? And these are all these proofs follow from like all the results follow from these Karp-Lipman collapses, which is like this win-win argument. I'll give you an example. Okay. So there's this Karp-Lipman theorem that tells you that if NP, right? If NP is contained in P poly, so there is like some kind of fast non-uniform algorithm that solves SAT, then the polynomial hierarchy collapses the second level. This is a no result. So let's see how this gives us low bounds. Let's prove this Kanan's theorem. It's very easy, right? And then we can just enumerate kind of n circuits. So I want to show that for any k, there's the polynomial hierarchy has a function that's not contained by this S. I can just find this function, right? Because it's a fixed k, I just go k plus 1, and I just try all circuits of that size. I guess the so I have two cases here. This one is NP is contained in P poly. That is here. Then the polynomial hierarchy collapses sigma 2p. I already have one function in polynomial hierarchy, so I'm a circle low bound. Case 1, I'm happy. Yeah? Okay. Case 2. NP is not contained in P poly. Because sigma 2p is higher than NP. So it's a win-win. In case 1, I win. In case 2, I win. And I'm going to both cases. Right? So circle stands. And so you can kind of generalize this argument. You can apply the same idea. And if you go back, what are the views? You need a class that's bigger than NP. You want to show that you want to put a class here that's bigger than NP. And you want something that is like smaller as to sigma 2p. And if you have those two properties, if they satisfy, you can apply the same argument here. And that's exactly what you have, like kind of STPs, you need like when the proof is low bounds for them, fixed point circuit low bounds. There are a couple of comments here. First of all, this kind of win-win arguments are non-constructive, right? There exists a function that's hard. I'm not giving an explicit function. I'm just saying that, like, by this win-win argument, there must be a function that's hard. So that's not like very pleasing. And moreover, you have the requirements of like what you want. So like if you want to like build and get like more interesting low bounds, like for other classes that are smaller, you need some new ideas potentially. Oops. Okay. So let me give you guys two real definitions, and then I'll show you what we prove. Okay. So the first definition is symmetric polynomial time. I think this is best shown with an example, so I'm going to go over here. What it says, so you have a yes prover and a no prover, okay? And you're a verifier. And you want to verify a statement. So you're given an instance X, and you want to verify whether it's true or false. What STP says is if the statement is true, there is a message the yes prover can send you that no matter what the no prover sends you, you always say yes. And if the statement is false, there's a message that the no prover can send you that no matter what the yes prover sends you, you always say no. Right? So they both send you a message at the same time. If it's true, whatever the yes prover sends you will guarantee you to say yes, no matter what the no prover tells you. And if it's false, then no prover can send you something that no matter what the yes prover sends you, will always say no. Right? So let's do the first case when X is when it's in the language. There's an irrefutable circle yes with a star that the yes guy sends, and the no guy sends anything zero. Whatever he sends, I'll always have a yes. The no case is I have a irrefutable circle with no, and whatever the Y guy says, yes guy says, I always have to know. That's the class. This is a little bit different than sigma 2p because in sigma 2p, the no prover can actually see what the yes prover says and then give a message. Now it's kind of parallel. Yeah, they were like kind of, so we went in the 90s, they had some crypto application, but it was really capture BPP. Like that's why they kind of defined this class. But it's not even a very powerful class. Like the constraints are quite big. Like this STP class is weaker than sigma 2p. Now we think it is. And it contains like NP, NA, NP. So it's a fairly powerful model. And we'll see how powerful this is in a little bit. Like so again, like as complexity theorists, when we find a class that's hard, we already have certain low bounds, we try inventing a new class where we can prove something, right? This is kind of third again. And so there's this other class called O2P, which is just the oblivious version of this. So it's a much more weaker model where again now we don't care what the instance is. I don't care what the satisfiable formula I'm giving you. I only care about the length of my formula. So I will give you if it's satisfiable. So all satisfiable formulas have a single yes star, a single yes certificate, and all unsatisfiable formulas have a single no certificate, right? So if I have a simple one, all yes instances, like it doesn't matter, it's completely independent of X. I have a single yes certificate and I have a single no certificate. So my verifier does not even care what X is. So the Y's are just independent of X. The Y star and Z star are independent of X. Does that make sense? In S2P, my Y star and Z star could depend on X. Now it doesn't depend on X at all. It just depends on the length of X. So for all X's of the same length, they have the same Y star and the same Z star. So that's why it's called oblivious. There's an oblivious version of S2P. Questions? Yeah.
It seems a bit like if it had a small circuit, you could just send the circuit and it would work for both cases, but I'm not sure.
But there is like the circuit idea is kind of right, but you can. O2P is a very interesting class because, well, one, the certificates depend only on the size of X and not X itself. And as a result, like, you can show that O2P is contained in P-poly. So the idea is right. It's also interesting that BPP is contained in O2P. So it's this class that's in the middle, like it's upper bounded by P-poly. It does contain BPP. So like if you can say interesting things about here, maybe you can say some interesting things about BPP. So this weird class that has some nice properties. And the best way uniform upper bound for O2P is S2P. So again, like if I want to do like lower bounds for O2P, I can't use this convolutional argument anymore because O2P is maybe smaller than NP. There's no like it's contained in P-poly, right? If O2P was an NP, if NP was contained in O2P, then you kind of already prove P is equal to NP. Right? So we have this class that's a little weird. It's been studied for a little bit. Can we prove like this really weak model? Can we show that actually this problem also is hard for non-uniform algorithms? Like there are languages here that non-uniform algorithms cannot solve. And this is interesting because if you look at the cognitive collapses, actually, if NP is in P-poly, the polynomial hierarchy does not collapse to O2P, as S2P collapses all the way down to O2P. you don't get circular bonds, you don't get circular bonds from there. Because exactly the kind of problems that happen in the second case, right? In the first case, you get your win. But in the second case, if NP is not contained in poly, I cannot say anything about OTP. Right? Because OTP is potentially a smaller class than NP. So I no longer have my win. So I have my first win, I don't have my second win. So again, we'll see how we can actually get lower bounds here too. Like that's going to be a result. Okay. Questions before I jump to results? Right. So our first result is just exactly this. We prove this fixed value lower bound OTP, this class OTP. Right? Why is this interesting? Well, first of all, we're the smallest class for which we can search it down. So now this is the frontier of these kind of lower bounds. It's constructive, so like we give you explicitly what the language is. So it's not like a win-win kind of, it's not a win-win existential language. We give you explicitly what this language is. It's the first clause about does not contain NP, right? So this is every clause before, like what I was saying, that Y's argument that is bigger than NP. This is the first clause where that's not the case. And it finally matches the collapse, the best collapse of the polynomial hierarchy. So like, in that sense, it's also satisfying. Best of knowledge, yeah. Best of knowledge. Okay, we prove another result, which is we give a hierarchy 0 for 2 time. Which is saying that if I have more time, I can solve more problems in this model. Again, this is interesting because this is a uniform hierarchy theorem, and we don't know any uniform hierarchy theorem for these kind of semantic classes. Like this is a problem, like these kind of semantic classes. And this class contains BP time, right? Like this is this big open problem, which is give me a hierarchy theorem for randomized complexity classes. We don't know how to solve this. Here we're given a class that contains BP time that is also like semantic. And yeah, it doesn't require any bits of advice. Like all the hierarchy theorems you know for these kinds of classes require one bit of advice. We're not able to get this without any advice. So that's also interesting. It's not clear that the techniques we use can be used for anything else. But it's a nice statement. Okay. Questions? So again, like we're very good at designing algorithms, right? So can we convert proving lower bounds into an algorithm design question? Right? So can we change the framing, trying to prove some lower bound into the framing of proving, like coming up with an algorithm for solving the problem? Okay, and that's this famous like range of awareness problem. So here's the problem. I give you a circuit that has n input bits and it has m output bits, where m is bigger than n. So my output space is much bigger than my input space. Okay? And when I have this, I'm guaranteed that there's something in my output space that's not in my there's something in my coordinate that's not in my range, right? My function maps to my fewer inputs, so there must be something in my output space that's not mapped to my input. And actually many, right? Because m is like, if m is n plus 1, I already have twice, my output is at least twice as big, right? And if m is like 100 times bigger, then it's 2 to 100 times bigger. Okay, so this, many outputs, give me one. Give me one output that's in my coordinate but not in my range. Okay, so this is again one of Papa Dimitri's favorite problems. And it represents the motivation of this problem was to capture probabilistic arguments. So all these expert construction problems like finding hot truth table, vision matrices, we all do why the probabilistic method. And it's like a random point is good, like, and so now you apply a union bound, and so like there exists such an object. Okay, and the figures in this video is there are 4 pigeons, there are 5 pigeonholes. There must be an empty pigeonhole. It's very important, like I said, the inverse Kabuto kind of principle. Surprisingly, yeah. Okay, so there are more holes and there must be an empty hole. That's what the word is in. Give me an element that's not in the range. The red lines represent my function, so the orange represents something that's not up with my function. Okay, but there's a very trivial randomized algorithm for this, right? I just guess. I guess something uniformly in my output space, and I just apply my empirical to verify. Guess and check. This will work with very high probability, right? Because my output space is so much bigger. But to come up with a deterministic algorithm is very hard. We're going to see some very interesting consequences. If you have deterministic algorithms that solve this problem, we get like very cool applications. And so we have a very easy randomized algorithm where like almost everything is good, like any random point is good. But deterministically findings at the point is quite hard. And this is exactly the hand haystack kind of situation we have with randomized problems. Okay, so as a result, I'm not going to get up to this. Like we get like conflict tables, and see, there are a bunch of different, like I just listed 3 here, but 9 codes, many different explicit constructions you get, this range avoidance. So if you could, essentially all it says is if you could solve range avoidance deterministically, you get a bunch of explicit constructions that we were looking for free. So this is like, just think of this one guy, think of this one problem, and that captures all explicit constructions. Or most of them. Okay. So let me show you how this works. I have some like bad object, right? Like let's say I want to construct a truth table that does not have circuits of size n squared, right? How do I do this? Well, I'm going to give a succinct encoding for bad objects. What is that? Well, I'll just give you the description of my circuit. How many bits are there? Like maybe n squared log n, right? Something like this. So I can encode my circuit in this many bits. How many bits is a truth table take? 2 to the n, expanding. And what is my decoder going to do? It's going to just take every input, parse the circuit, and value in every point. So it gets a big truth table. Right? Now what I'm going to do, like all my bad objects, all circuits of size less than n squared are captured in my function. So if I saw a range avoidance on this circuit, then I do the truth table, like any solution is a truth table that doesn't have circuits of size n squared. Makes sense? And this is the same argument that works for like range matrices or anything else. I come up with a system encoding that encodes all my bad objects. And so when I solve range avoidance, I'm left with a good object. Oops. Huh? Yes.
Generalization of diagonalization.
Yeah, this is exactly like that. Yeah. And that's intuition for our thing too. It's finding what the compressor is, right? Like the compression, like in these reductions, the hard thing is like finding the compression of the object. Once you have that, then you're just diagonalizing against it. Okay. So as a creator, now we're kind of like, so if you could solve, there's one issue here, which is that when I solve a void as a blanket, there are many solutions. There's not one solution, right? Because there are many elements in the output space that are not in the range. So if I just had an avoid oracle, any solution would be good, right? But all my physical constructions, I want like a single solution, right? So if I have access to not just an array, I have access to a single value array, then I can start constructing these hard truth tables, right? Because now I just construct my word instance, and whenever it spits out like a single value, that's my answer, right? That's my language. S's are the ones and the no's are the zeros of my language, right? So the truth table can encode my language for any fixed length. It's crucial that I have a single value here, otherwise my language is not well defined. Okay, so if I have this, then I'm happy. If I have a local for a single value array, I start doing all kinds of crazy stuff. And turns out that this is exactly what was given to us in like last year's talk. So Zhang and in this paper, and like I think this is CHR. So I think Alan, Suchi, and Vijay, I think they proved this paper. They give a single value S2P algorithm. So that was weird complexity class, but like this weird complexity class has a single value algorithm that solves the problem. So maybe as a byproduct, they get that S2E has maximum circuit complexity, S2P has circuit for fixed polycycle low bounds. Right? And so now we're just going to like kind of modify this for our needs to get our results. Okay, questions. So what are we going to measure? But first, we don't care about this E region, we care about this fixed point region. So we want to work in a smaller region to see what that looks like. So we want to define and we want to give the language from our word instance and argue that there's some properties of this language that are actually that make it amenable to like also becoming oblivious, like belonging to O2P. So it's not an S2P language. We show it's an S2P language. We show that like actually this language is an O2P. That would give us a load one. And once we have like it's an O2P, then we want to just use the fact that O2P is upper bounded by the poly, and there is a circuit size hierarchy theorem. And we can lift the circuit size hierarchy theorem, we get a hierarchy in O2P. So that's basically what we're doing. And let's see some small things. Okay, so let's see how like what this would look like in concrete. So like, let's say I want to prove for some k. Pick the k characterized, like k is equal to 2. I want to show that there's no truth table with size n to the circuits is exactly what we're talking about. Before, I'm going to put all circuits of size n squared in just n square log n square bits. And now I want to be really careful because if I just take the truth table of C, that has 2n bits, I'm going to now just pick like first, let's say the first like s log s plus 1 bits, right? So this way, like now my construction is completely polynomial. Now it's like my whole structure is polynomial by exponential. And I just define my language as whatever comes out of a void, coming with a bunch of zeros at the end. This is my language. Okay, first conclusion. If I solve a void, immediately I get a truth table. This k, whatever this truth table I get over here, has no circle the size under the k. I'm guaranteed this. But again, every time I call a void, I get a different solution. So if I have single value a void, if I apply the single value STP algorithm, I now get a specific language, right? It's not well defined because I always get the same. My prefix bits are always the same. That's the whole point of the single value. And the main observation here is that like this is very, very sparse, right? Because the bulk of the language is a bunch of zeros at the end. Right? So like which we can we somehow use like sparse STP languages in O2P? Can we kind of show something like this? Okay. And like to do this, that's exactly what we show. We show that like if a language is like we define this notion of uniformly sparse, but like it's a sparse language, which means that there are very few guess instances, like polynomial many. And it's also in P. And we say that a language has a uniformly sparse extension when I can embed this like my LK, like I can embed my language into a uniformly sparse language. So the uniformly sparse language is super easy. It's a way of tapering out like many of my points. And if I can embed my whole language into some uniformly sparse language, I say that a language has a uniformly sparse extension. And once you have this, you show that like a language in S2P with this uniformly sparse extension is also an O2P. And then you can just see that the language that comes out of this word reduction has this property. And then we get that LK belongs to O2P. And then everything else follows from there. It's very standard. Okay, everything follows. And then I'm done. So can we show that every sparse language, like we need this uniformly sparse extension, do we really need that? Can we show that any sparse language in S2P is also an O2P? Question one, that'd be interesting. I don't know how interesting. Maybe more interesting is like this PDNP, can we prove PDNP load bounds for this is a big problem. Like, can we show that if we can show that O2P is contained in PDNP, then we get this one way of filling these PDNP load bounds. Or we can show that O2P is contained in MA. That's one way of going out without needing this one bit of advice. So if we can show containment of O2P in any of these bigger clauses, we get these fixed value load bounds. And then like again, like load bounds of smaller clauses like OMP, but this is not so interesting. All right, that's all. Thank you.
Okay, the speaker was generous enough to answer many questions already during the talk, but if anyone has any more questions, we can. Yeah, please take it.
Maybe you already answered this. I think change the symmetric exponential time is infinitely often is used.
So this is stronger than so they had the infinitely often in the chain here, but then the lead is off.
Okay.
I see.
Okay, any more questions? Let's stand and speak.
Thanks. Will it work? Yeah, should work. Yep.
Okay, the next talk, better boosting of communication oracles or not, is by Arthur.
Back with this one, and this is the pointer.
Okay, thank you for the introduction. So, yeah, this is talk about better boosting with communication oracles or not with Nathan here. And yeah, so let me give you an example. So suppose you have two algorithms, one which computes the same function. One is a slow and deterministic, and another is fast, but it's randomized, so it works only with probability 3/4. And it's suppose it's independent for the runs. It's not probability over inputs, it's probability over the random bits. Okay, and when you want to compute the sum of this function over the values from 1 to n, and obviously you can do it using slow deterministic algorithm, but maybe you want to do something faster, so you replace the slow algorithm, fast algorithm, so you replace the slow one with the fast one, and okay, obviously that wouldn't work, right? Because if you make even a single mistake, that all will screw up your sum. So what you can do is you can do majority vote, right? So you can run your algorithms about logarithmically many times and take the largest, like the value which occurs the most frequent, right? So majority is the value which occurs at least half of the times. Okay, so the question we asked is this the best you can do? Like in what scenarios you can do something more smart than just running algorithms about logarithmically many times and then taking the majority, right? Okay, so this question is very hard to answer in the negative if you're really talking about algorithms. So I will talk about communication complexity. So in communication complexity, you can like ask this precisely the same question, right? But before doing this, let me first define it. So in communication complexity, we have a function. Let's suppose it's like a Boolean function. So it has two inputs, and one input goes to Alice and another goes to Bob. And then they want to compute this function by communicating bits between each other. Right? So in the end, they want both to know the value of the function on their inputs. Okay, so let me give you a simple example of such a function where this communication complexity makes sense. It's called equality. So in equality, Alice and Bob are given these inputs, and they want to output one if and only if their inputs are equal, right? So what they can do is Alice can just send Bob X, and Bob can send her back whether this X and Y are equal or not. And this is very costly. It costs like basically as much as as computing any function in communication complexity. It's like to encode X, Alice needs log n bits, so it's logarithmic costs, which turns out to be like the largest you can have in communication complexity. Okay, but then maybe we can do better. So, and we can do better if we have randomness. So if we have like a flying string of random zeros and ones, like flying in the sky, Alice and Bob can utilize it to improve this protocol drastically. So they can interpret this string as a string of 0, 1s, 2s, and 3s, and Alice can look at the X bit in the string, and Bob can look at the Y's, and they can exchange these bits. And oh god, this is okay. This is this weird system. Yes. Okay, yeah, so they can exchange these twos between each other, and you can see that in that case, this protocol doesn't work. So it's if these values were different, right, then Alice and Bob could conclude that X and Y are also different. But here, it's an annoying case where they turn out to be equal, so they output wrong value, and yet it's easy to see that this happens with only probability 1/4, right, because these values are random. Okay, so we go from maximally hard to basically minimally hard function if we introduce randomness. So this again illustrates that maybe you have a slow deterministic algorithm, but very fast randomized one. Okay, so let me illustrate, give you one more example, like an illustration how you can use this equality function as a subroutine for another algorithm. So this another function we want to compute is probably like well known to everybody. It's called longest common prefix, and in there Alice and Bob are given two strings, and they want to compute the length of the prefix of the strings which coincides for Alice and for Bob. So this green thing on the slide. Okay, so how can they do this? yeah, they can do the same protocol which works for every function, that is can send her string to boot or something like this, but this is very costly. So instead, they can compute, they can perform binary search. So they can ask the halves of their strings equal to each other, and they can, for example, they can engage in the perfect equality protocol of Alice sending the string, so they can get that these halves are not equal. Okay. Then in binary search we go lower, we go to the quarters, they turn out to be equal, we increase slightly, it's still equal, we increase it some more and it's still equal, and increase it some more and it's unequal. Trust me, it was a binary search, not linear search. Even, I mean, it was just a weird coincidence, but in the end, we gain that we have like one prefix which is equal and the next is not equal, so we know the value precisely, right? Okay, but that only assumed that we had perfect access to what I call equality oracle, so perfect subroutine which computes whether the strings are equal or not. Okay, what if we don't, right? What's like if we use instead the fast randomized algorithm that we had, these equalities, I'm sorry, inequalities might turn out to be equalities sometimes, right? Which is not great because binary search will go completely wrong. Okay, so instead we can repeat this query to our non-efficient procedure several times, as we have done in the previous slide, and that way we can again take majority vote and succeed. Okay. Wait. Okay, we can, I guess, yes, so the question I'm trying to answer on this slide is how can we do better? So we can, equality oracle turns out we don't need to incur any additional logarithmic overheads, and we can do it precisely like in linearly many queries to the imperfect equality oracle. So it's almost classical. So we can view, for example, binary search as this decision tree which asks equality queries and in the end returns the length of the common prefix, but it works for every function which is computable with this equality oracle queries. Okay, so there are two ideas that we need to make the beta boosting work. So the first idea is that we have one-sided error. So if we get not equal, we know that the strings are or numbers are really not equal. And the second is slightly more advanced, but not so much. It's that we can check whether the equality is true by performing just one equality query. So if we want to double check our previous equality answers, we can just concoct like two strings, send them to equality oracle and check that all these queries were correct or not. Again, we might receive an error, but we will deal with this in a minute. Okay. So, right, so how much time do I have? Okay. Right, so, okay, so let me simplify this tree. So the way we're going to do is we will perform a walk on this tree in search of the right path of the computation. This is classical algorithm, basically classical algorithm due to Nissan for greater than, and our contribution is that we like make it more sort of general, slightly more general. And yeah, let me present how it works. So we just make a query. Yeah, sorry. So suppose this green dot is the right answer, so it's the right track of the computation given the perfect equality oracle. So let us try to use the imperfect one to reach this green dot. So we will make a step. So we will ask the query in the root. It turns out to be equal, so it's on the right track. We do it again. We double check whether this query was indeed equal. Suppose the double check turns out true, and we proceed, but then we proceed by one step incorrectly, right? So maybe we got the wrong answer. So we are off the right course. Maybe it happens again, like our double check doesn't help us, and we do this erroneous step again. But then we do the double check, it doesn't work, so we track back. And this is the key idea. We just backtrack if our double check doesn't work. So maybe we have done this again and we double backtrack again, so we on the right track, and then everything happens successfully and we end up in this green dot. Okay, so how do you prove that this actually achieves what we want, that it's just linear blow up? You can view the steps as good steps and bad steps. So the bad steps is either we correctly backtracked or we were just on the right path. And it's easy to see that if we made like depth of the tree more correct steps than incorrect steps, we reached the green dot. So we reached the right path of the computation. Okay, so we can assign to these steps +1 or -1 score, and if you achieve score depth of the tree or Q, the number of queries, you are in the money. What?
It has become black there.
Did it? It's almost black, but I can see some stuff over there, so you can look there. Maybe it's too little light. Yeah, sorry, the black and white styles don't work at all. Yeah, so anyway, so you have some score, and if you gain at least some score, you win, right? Okay. So how do we analyze the probability of this? So we have these random variables for each step. We have either +1 or -1 of some probability. And what is this probability? With at least 3/4 we succeed, and with 1/4 we fail, right? So the expectation turns out to be half, and then we just apply Hoeffding inequality to get, or your favorite condensation inequality to get the probability bound, right? Unfortunately not, we cannot apply the classical concentration inequalities here because this size are not independent. Like from the previous steps may affect the subsequent steps. So there are like some examples of this, but this is not a huge deal. I just wanted to highlight this. We can still use some slightly more sophisticated condensation inequalities by just observing that conditional expectation of one variable condition on every other variable is at least half. Okay, so some slightly more sophisticated condensation inequality works. Amazing. So in summary, this is a generalization of result of Nielsen, which is saying that if you have a function f, which is computable by k equality or q, equality oracle calls, then it can be computed with randomized cost big O of q. Okay, so this is the better boosting for equality oracle, right? So we didn't have to boost the error with majority vote. We have done something smarter, and we just got the faster randomized algorithm for free. Okay, so the main question of our work is not that, it's what happens for other oracles. So can we do it for something else and not equality in the communication setting? So yeah, so the first thing we show is that the same exact protocol doesn't work only works for equality. Like it's not hard to see that like it's for no other function. Basically, you can you can double check several instances of it with a single query. It's I think it's a nice exercise, so I will not comment much. And so the more, but this is not really satisfying, right? So we want something more strong. We want to say that for other oracles, we need to use this something like majority vote, right? So to that end, we consider this function Hamming distance 1, which asks for x and y if they differ in exactly one position. So this can be thought of like the next simplest thing after equality. So there are some formal ways to sort of to say it. So, but let me just leave it at that for now. This is just equality is Hamming distance 0. This is Hamming distance 1. So what happens for that? Okay, so first let me observe that Hamming distance 1 also has randomized communication cost constant. Okay, how to see this? We can look at like Alice and Bob have inputs, they differ in one position. So how do we check that they are Okay, if they differ at 1 or 0 positions, we need to return 1, and if they differ at more positions, we return 0. So the idea is that we partition the bits randomly. So here's like some weird partition, and if the inputs differ in 2 or more positions, then we see 2 inequalities, like the substrings, both substrings will be not equal if we put 2 positions in different subsets, right? Two different positions in different subsets. So here they differ only in 1 position, so every time we just get 1 inequality and 1 equality, right? Okay, but if they have differed in 2 positions, like here, then, like if we are lucky, we can get this situation where it's 2 inequalities. Okay. So with probability half, we do this, and this exact algorithm can be generalized to arbitrary k. You need to partition into k-squared subsets to achieve the same effect. Okay, so yeah, so where were we? We were trying to see if Hamming distance 1 oracle has the same property of beta boosting as equality. So yes. Okay, so we've proved that Hamming distance 1 have a constant cost. So the question is that if we have a function which is computable with some number of Hamming distance 1 calls, then we do the same thing we have done for equality and just come up with a protocol which have communication cost big O of k. Okay, so the answer is no. And we prove that, in particular, if you just need to compute the value of k copies of Hamming distance 1, you already need k log k randomized communication cost. So it means that nothing better than majority vote is possible for Hamming distance 1. So yeah, so let me comment that Blair and Brody, so this can be sort of, I don't know, super critical direct sum theory where we need like more than the total cost of all problems to compute them all, right? So it was first done by Blair and Brody. They come up with a function which has this property that you need like super linearly many computational costs to compute k copies of the function. Okay, so yeah, but for us, the more important corollary is that the answer for our question is no. So it's not possible Hamming distance 1. And the second slightly more surprising corollary is that Hamming distance 1 requires log n many deterministic equality oracle pairs. So notice that our protocol was like randomized reduction to equality, but if we want deterministic reduction to equality, we need logarithmically many queries, and this is achieved easily by combining like the beta boosting for equality and the lack of this boosting for Hamming distance 1. Okay, so yeah, so now I want to present our main proof. How much time do I have?
10 minutes.
Okay, this is very easy proof, so I will manage. Okay, so yeah, so we want to show that computing Q copies of Hamming distance 1 requires Q of Q randomized communication cost. So how do we do this? So we stand on the shoulders of giants, in particular the giant named Saglam, who proved in 2018 in like a giant tour de force that Hamming distance k requires communication cost k log k. So Hamming distance k is the same as Hamming distance 1. We need to check that 2 strings given by 2 Edison different at most k positions. So this requires at least k log k communication cost, which is a very complicated theorem, and our proof is a reduction to that. So we prove that Hamming distance k can be reduced to linearly many queries computing linearly many copies of Hamming distance 1 several times. Okay, so let me demonstrate how it's done. It's basically the same idea as the constant cost protocol for Hamming distance 1. So we have some strings which differ in some positions, the red ones. So what we do, we partition them in about linearly many parts, linearly many in k, and we have the procedure which computes k copies of Hamming distance 1. So we feed these parts to this procedure. Okay, so we get some answers. So we get answers 0 if they're equal, and we also can run like equalities for every of the strings. And we can we can have the information that some parts at distance 0, some parts are at distance 1, and some parts are at distance 2 or more, if we get like 0 answers from having distance 1 inequality. Okay, then for the strings which are distance 0 or 1, we already know the precise distance at that subset of the bits, so we can discard them. So we can remember that we have a distance at least 1, we can discard all this green stuff and only deal with the red stuff. So, and then with the rest, we just do the same, just partition, we run this routine which computes having distance of k copies, we discard all the green stuff, and we continue. Okay, so why? So roughly, why does it work? Because we can save on error boosting here. So we can compute k copies of having distance 1 with error 3/4, and with error with probability 3/4, all of these queries will be correct. So we have like much better. We don't have to error boost every having distance 1 query. We can error boost these guys together, and it is beneficial. Okay. So let me, I have more animations, but they're the same. And let me, yeah, okay. So we have proved that we can reduce having distance k to k copies of having distance 1. And that concludes our main proof. So the open problems here, like the first one is, can we do this for, like, it's not quite satisfied. So we have some reasons to think that having distance 1 is like the next problem after equality, but it's not provable. It's just we don't know any examples. Like I mean, we as humanity doesn't know any constant cost problems such that they're like in between equality and having distance 1. What I mean is that like it's deterministically not reducible to each other in constantly many oracle calls. So maybe this beta boosting is characterization of equality. So maybe there is nothing in between. Or yeah, so maybe there's something in between for which we can still show that there is no beta boosting possible. And I guess more generally also you don't have to only focus on constant cost communication problems. So for example, for greater than, we can show that beta boosting is possible simply because it is its best protocol is just deterministic reduction to equality. And but the question is, maybe that's not the extent of all possible examples where beta boosting is possible. And I have. Yeah, so the last problem is whether we can find like this phenomenon where we require like super linearly, where like this there's no non-trivial boosting for some function which is Boolean. So our example function was not Boolean, it was direct sum. So it will be satisfying to find an actually Boolean function. Okay, that's it for me. Thank you.
Any questions? Okay, I would like to ask something. Please go to the proof of your theorem, that part. So, thanks. So what if we want to do something like HT and under root something between k and 1? How would that change the bound order k?
So again, so k is, you want to specify the relation between k and n.
Yes, yes.
So I think the bound until the sublime proof works is I think square root of n. So that's and I think maybe it's even might be even tight. I'm not sure.
Oh.
So our proof consequently doesn't work as well.
Okay.
Yeah, so I mean yeah.
Okay. Let's thank the speaker again, please. So this brings us to the end of this session. I think we have something else, huh? The young researchers meet or something.
কিছু করতে হবে, shut down লাইটটা বন্ধ করে দাও সেটা আমি বন্ধ করতে পারছি না তো কিছু escape টেপার কিছু ব্যাপার আছে এটাই করার চেষ্টা করছি জুম সেশন ওরা end করে দেবে কেউ একটা end করে দেবে সেটা এটা তো আমরা তো end করবো ঠিক আছে